All right, lecture about gravity. Here we go. We talked a lot about motion overall. Newton got a lot of airtime because he contributed a whole lot to understanding motion of objects on our everyday scale, level, and even planetary objects. So yeah, we've kind of been dancing around or assumed a bit about gravity, that you understand that there is a gravitational force, and that force, due to Newton's second law, accelerates objects towards the center of the Earth. Yeah, so now we're finally going to talk in a decent amount more detail about the gravitational force itself. One of the things that Newton is, one of the reasons he's so well thought of and known to this day is, as you might already know, is his theory of gravity, or understanding how massive objects pull on each other. One of the sort of ways that he maybe came about this, not exactly sure how he did, or I'm not, but is that if you understand that the moon rotates around the Earth, and from our previous lecture about rotation, if something's going to rotate around in a circle like this, then there needs to be a force acting towards the center of that circle. So if the moon's rotating around the Earth, there needs to be a force on the moon towards the center of the Earth that keeps it rotating that circle. Right? That's the centripetal force. And Newton sort of realized that, well, it's the force that's keeping us on the ground that pulls you down to the ground if you jump up in the air. That's the force of gravity. And it's actually the same force that's pulling the moon towards the center of the Earth as well. And he also discovered that gravity actually gets weaker as you get further away from the Earth, or in general further away from a massive object, the weaker the gravitational force will be. Before Newton, and for a long time in human history, it was essentially thought of that, well, we live on Earth, things are the way they are here, and there's this other sphere, the rest of the world, or whatever, the rest of the universe, whatever you want to call it, the stars, the heavenly bodies, they had all kinds of names for these things. But for a long time, it was thought that the heavens essentially worked in a different way than things on Earth did. Right? Things on Earth worked one way, things up there worked differently. And so you kind of, worked off of that assumption for a long time. Something else that Newton is really, it's similar to the last slide, that Newton's very well known for, and it's actually called Newton's great synthesis, is to discover, to postulate at least, that no, the things out in the sky, the stars and the planets, and the things that we see out there, they're actually acting according to the same laws that are in force here, right on the surface of the Earth, right? The same laws that govern things here are the laws that govern things out there. So it's no longer two sort of spheres of physical laws, or any sorts of laws. It's actually just all one of the same thing. So essentially the same set of laws applies to the stars as it does to planets and it does to people. And one of those laws, one of the ones that Newton is well known for, is what we call the law of universal gravitation. And put very simply, the law of universal gravitation just says everything pulls on everything else, specifically everything with mass. Right? So if you have a massive object and you have another massive object, those two things will pull on each other with the gravitational force. Though, as we'll see later on, the gravitational force is in fact very weak, so it takes a very large amount of mass in order to develop a significant gravitational force that we might actually feel. So something the size of the Earth is very, very large, so it's large enough mass that it creates a gravitational force that has a noticeable effect, namely pulling us to the surface. Whereas, a baseball has mass, it also has a gravitational force on other objects around it, but it's very, very weak, so you don't ever really notice it on a day-to-day basis. So Newton said that every body, meaning massive body, attracts every other body with a force that is directly proportional to the product of their masses, so multiply the two masses multiplied together, and inversely proportional to the square of the distance separating them. So 2 factors of the distance separating them. Let's look at that a little more closely then. So that was in words, if we try to start putting that into proportional relationships, we would say that the force of gravity between two objects, say object 1 and object 2, or mass 1 and mass 2, is proportional to the mass of the first object. So that mass goes up, the force of gravity between the objects goes up. It's also proportional to the mass of the second object. Again, that mass goes up or that mass goes down, the force will go up, the force will go down. And it's inversely proportional to the square of the distance between those objects, right? So proportional to 1 over the 2 times the distance, or the distance squared, sorry, not 2 times. Distance times distance. So in a diagram sort of fashion, you'd have one mass, you have another mass, and the force of gravity between these is pulling towards each other, right? That's, again, everything pulls on everything else. They're always pulling towards each other. The distance we're talking about here is technically the distance between the center of masses of the objects. And yeah, that amount of force is going to go up if either of the masses goes up, and it's going to go down if the distance gets larger, right, because it's inversely proportional, and it's going to go up if the distance gets smaller. It's inversely proportional. And in fact, the force of gravity from, say, mass 1 on mass 2, right, the force pulling it there, is the same amount of force that mass 1 pulls on, or mass 2 pulls on mass 1, right? So these are actually equal and opposite forces, straight out like Newton's third law, right? There's this mass pulls on this mass reacts by pulling the same amount on this mass in the opposite direction. Okay, so what's the exact formula for the force of gravity? Well, it turns out it's all those things. It's mass, the first mass times the second mass divided by the distance times the distance, or the distance squared. And if you want to put it into an equation, it turns out we need this factor of g, this number g. And through experimentation, through figuring out what the force of gravity was between two objects, we could experimentally find out what the value of g is. So what is it? Well, g is what we call the universal gravity constant, and that's what it is. 6.67 times 10 to the minus 11th, and the units are Newton meter squared per kilogram squared. Again, we're not worrying too much about units here, but that's what they are. And also, we haven't worried too much about exact numbers either for the most part in this course. So the reason I'm showing you this is not because I want you to memorize this number or the units to go along with it. It's the fact that it's very small. It's almost a trillionth of whatever those units are. It's a very small number. And that gets at the fact that I was saying earlier that the force of gravity in general is actually very small, which is why you need a large mass, or large masses, in order to actually have a noticeable effect. The force will be large enough to actually kind of cause things to move. So I would just point out that this is called the universal. So right now, this is universal. This is how everything, or gravity acts the same everywhere. As it turns out, we're going to learn a little bit later that gravity in a more detailed sense was explained by Einstein with his theory of general relativity. And from that, Newton's theory of gravity is essentially gravity when things aren't extremely massive or extremely dense, and when they're not accelerating very fast. So for us, no, we never really do that. We don't experience anything like you need black holes or things of that nature to really get away from where Newton's gravity would still work. So vast majority of the places, universal gravitational constant, this is it. And that formula for the force of gravity between two objects, perfect, works perfectly. Okay, so we're just going to walk through a sort of sample problem. It involves, using some pretty big numbers with the scientific notation. So if you're not too familiar, don't worry about it too much. It's more of an exercise to see what comes out of this formula. So for instance, if we took two masses, one mass being a 10 kilogram piece of iron, the other mass being the Earth, right? What's the force of gravity between those objects? Well, We know what the mass of the iron is 10 kilograms. I'm going to tell you what the mass of the Earth is. And then we need to know the distance, meaning the distance between the center of the iron and the center of the Earth. So essentially the radius of the Earth. I'm going to tell you that as well. All right. So here you go. That's Newton's equation for our gravitational force. It's equal to G, and I put G in there, multiplied by mass 1, 10 kilogram thing of iron, mass 2, the mass of the Earth, which is a very large mass, divided by the distance between these objects. The distance between the center of the iron and the center of the Earth is essentially the radius of the Earth, so just put in the radius of the Earth there. Again, pretty large. But if you put all these numbers into a calculator correctly, what you'll get is about 98 newtons. The units turn out to be newtons, it's force, right? Or about 100 newtons. So why is that significant? Well, forget all about gravity for a second, or the details of gravity that I just told you about. If I were to tell you, or ask you to find the gravitational force on a 10 kilogram piece of iron, hopefully you would remember that the force could be calculated as that mass multiplied by the acceleration due to gravity. And I told you a long time ago in the beginning that acceleration due to gravity is 10 meters per second per second squared. So 10 kilograms times 10 meters per second squared, ta-da, you get 100 newtons, right? So we get the same result here as we did with the much more complicated formula. So why even bother? Well, why the much more complicated formula is because this is can be used for any masses, right? When you use the fact that the acceleration due to gravity on the Earth's surface is 10 meters per second, that's a very particular thing. That works on the surface of the Earth. Even if you move up into the stratosphere, it changes a bit. Right? So this equation tells you the force, gravitational force between any two objects. And essentially what happened when we plugged all the numbers in for the mass of the Earth, the distance, the radius of the Earth, and G, right? All those things essentially combine together, and on the surface of the Earth, we're at the radius of the Earth, the edge of the surface of the Earth, then all those things combine together to essentially give you that 10 meters per second squared. So this is also why, like I said, if you go far enough away from the Earth's surface, then you're getting pretty significantly different than just being the radius of the Earth, right? Like if your Earth's center is here, there's the Earth's surface around it. If I move far enough away, then the distance now in this formula is significantly larger, and the force is going to be significantly less, the force of gravity from an object out here. All right, so there you go. That was an example of calculating the force of gravity between the Earth and a chunk of iron. You can do it between any two masses. And again, anything that's massive is going to pull on anything else that's massive, and you can calculate the amount of that pull using that equation for the force of gravity. Right? G, mass 1 times mass 2 divided by the distance squared. The fact that gravity, the force of gravity, kind of falls off or becomes less intense as the distance between the objects gets greater, right? It's inversely proportional to the square of the distance between the objects. So the greater the distance, the weaker the force of gravity. This is an example of what we would call an inverse square law. In general, this is just a term for something that acts exactly like that. If you get further and further away from the object, the effect or the intensity from that object will get weaker as the square of the distance. Meaning if you go twice as far away, then it will have fallen off 4 times. If you go 4 times as far away, it will have fallen off 16 times. Right? So whatever the square of the distance is, that's how it's falling off. So this is how we would write a general sort of proportional relationship for this kind of inverse square law, where the intensity of something is proportional or inversely proportional to the square of the distance. And just to point out that what that means for gravity is that even if you get very, 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 very far away, right, the distance gets very large, that means you're getting the intensity of the force of gravity is going down quite a lot, but it never actually goes to 0. So even if you go very, very far away, essentially you're just dividing by a very big number, and you get a very small number, but it's not 0. So even very, very far away from the Earth, there is still a gravitational force from the Earth. It's just incredibly small. So let's think for a second about why this inverse square law is what it is. It's not just gravity that follows this inverse square law. The electric force follows an inverse square law. The magnetic force, to some extent, follows an inverse square law. A lot of things follow that sort of pattern, where if you move twice as far away, the intensity of it will fall off by a factor of 4. And one of the the reason essentially for that is that it really comes down to geometry. It comes down to the fact that if I start out with, say, a balloon, and it's a certain size, right? It's this perfectly spherical balloon. If I double the radius of that balloon, well, then the material that is making up the balloon has to stretch, and it gets thinner. So essentially, as I kind of stretch out that material, there's less of the material in any given spot when I stretch it out. So if you try to expand this sort of spherical volume, then whatever is on the surface of it, like the intensity of that sort of thing, spreads out more and more as you expand that surface. So one way to think about this is if I were to take a can of spray paint and spray a certain section of something with this can of spray paint. I have a certain amount that I spray, and I guess once 1001 or something like that, I count for a second and I spray that out. Then if there's a surface that's at 1 unit distance, say like 1 foot away, I spray that spray paint, it's going to cover that surface with a certain thickness of that paint, right? Because it's whatever amount of paint that comes out just covers all that surface, and it covers it evenly, assume it's evenly, right? So you get this even layer of paint with a certain thickness. Now, take that surface and move it back, and it turns out that if you were to try to spray that same amount of spray paint, well, it's going to expand more and more as it goes out. It's going to go out to 4 times the area when you double the distance, and the layer of paint is going to go down by a factor of 4 as well. Since you essentially took that area and you spread it out 4 times, the thickness of that paint has gone down by a factor of 4. And then if you go, 3 times the distance, you're 3 feet, whatever it is now, away, then that spray paint will have spread out even more, right? And we'll actually end up with 3 by 3 square to cover that thing that the spray paint would get out to. And now the same amount of spray paint would cover that area, but it would cover the area with a layer that's 1/9 as thick. So this is essentially the thickness of that spray paint that's sort of covering these surfaces is falling off as the square of the distance away from the spray paint, or from the can of spray paint. You go even further, go out to 4 times the distance, then it spreads out over 16 times the area, and so the layer of spray paint is 1/16 as thick. So yeah, so gravity, the force of gravity acts in a very similar way in that if you were to go 4 times as far away, the force of gravity you would feel from this object would be 16 times weaker, or 1/16 of what it was when you were closer here. Yeah, so one thing you can, I'm not going to do it right now, but you can do this pretty easily yourself, is actually, you can see the sort of geometry of this inverse square law by just taking a regular sheet of paper, or two regular sheets of paper, and you fold one in half, and then in half again. So you have a full sheet of paper, and then you have a fourth of a sheet of paper. And if you hold them next to each other, well, obviously, if you're holding them next to each other, this one's going to be 4 times the size of the one that you just folded. Right? And what you can do is take the full sheet of paper, right? So take that full sheet of paper and extend it out, close one eye so you get a better perspective on both of them, and put it as far enough out so that it appears to be the same size as the folded sheet of paper. Right? And you can overlap them a bit too. It becomes easier to figure out when they get to be the same size. And as it turns out, since this one is 4 times the size of that one, it's going to be about at twice the distance away from you. The area that paper takes up in your vision will be 1/4 of what it is when it's here. So this is another example of an inverse square law where I have a certain area that I'm looking at, if I double the distance away that it is, the area that it takes up now is 1/4 that it did, or 1/4 that it was up here. And so now I can compare it to my 1/4 that was still at that same distance, and you'll see that twice as far away, it's now 4 times as small. Yeah, okay, so keep going with some interesting things about or having to do with gravity. For one, thinking about just what is it that happens when, say, like an astronaut in the International Space Station, why is it that they seem to float around, right? It doesn't seem like gravity is acting on them. It seems like they're just kind of hanging there in the air and doing whatever they want. We've seen videos of that already. And if you're actually very, very far away from the Earth, where there's essentially the Earth's gravitational force is nil, it's not really pulling on you at all anymore, then you get the same sort of effect. If you're far enough away from all gravitational sources, or masses essentially, then you get that same sort of effect where you're essentially weightless, right? You're not feeling the force of gravity in any direction. But these astronauts in the space station, it's not the case that they don't feel a force of gravity, or that the force of gravity is not acting on them. It still is acting on them. In fact, it's only about 10% less up there in the space station than it is down here on the Earth's surface, right? So remember, get further away from the center of the Earth, that's the increase in distance in our force of gravity formula there. So you get further away, the force of gravity goes down. But again, the radius of the Earth is so large that even up in orbit, it's not that much of a difference. It's only about a 10% difference that it amounts to. So why is it that these astronauts feel weightless? Again, it's not because there's no gravity out in orbit. There's still 90% of the strength of gravity, or that force of gravity is still out there, right? Or out at that distance. What it is that those astronauts are in a state of what's called free fall, meaning they're falling, essentially, is the easiest way of saying it, right? And we feel a state of free fall in a number of different places, but if you're, say, in a elevator, right, and the elevator is just holding still, then you're feeling the force of gravity because it's pushing you down and the floor is pushing you back up. If the elevator failed somehow, and elevators have an incredible amount of safety features, so that very unlikely to happen, but if they all failed and you start falling, well, gravity's still pulling you down, but now there's no longer a support force pushing you back up, so you essentially don't feel any weight anymore, right? So now you're in a state of free fall and you feel weightless. Same sort of things happen if you just go cliff diving or something like that, right? For that moment that you're in the air, gravity's still pulling you down, but there's essentially nothing resisting that pull, or no support force or anything like that, so you don't feel any weight, right? In the same way, the astronauts out in the space station are falling towards the Earth, but essentially just missing the Earth. So they're also in a state of free fall, which is why they're weightless. Okay, so another thing about gravity is that, like I've mentioned, the force of gravity we need to know the distance between objects in order to calculate the force of gravity between those objects. And I've said a couple of times that distance is actually measured from the center of gravity, or the center of mass of the object. So what is that? Well, the center of mass is essentially just the average position of all of the mass that makes up the object. The center of gravity is actually technically slightly different than the center of mass, but for our purposes, they're essentially the same thing. So we're not going to worry about it. I might say either one, but I mean the same thing. It's essentially the center of where all the mass is, or I think we'll look at the next slide. If you were to put that object, whatever it is, on like a tiny point, and that point is under the center of mass, then the object would balance. So it's kind of the averaged out place where all the mass. So like if you wanted to locate the center of gravity of an object, well, take the object and put it on like your finger, or put it on a point of something, and once you get that object to balance, then your finger is directly under the center of mass. So you can do that with like a meter stick or a ruler, and if they're uniformly or pretty nicely uniform rulers, then the center of mass is probably going to be right pretty much in the center of the ruler. for something like a sword, swords are forged so that the center of mass is not in the center of the sword. It would be very awkward if it was. The center of mass of the sword is generally tried to put right above or right at the hilt of the sword. Makes for a much more balanced sort of thing because you're actually holding it right there. So generally, it's balancing right on your hand. So when the center of mass or the center of gravity, same thing for our purposes, when that thing is over the base of an object or the surface of an object that's resting on some, or the face of an object that's resting on some surface, when that center of mass is over that base, the object is what we call stable. It's not going to fall over. So in the picture here, if you have two different objects, one is this like straight rectangular object. It's all this uniformly distributed mass. So the center of mass, or the center of gravity, is just right in the center of the object. And there you go. The center of gravity is over the base. The object's stable. It's going to be fine, just chilling right there. Whereas if you take this other sort of brick where it's now more of like a parallelogram shape, again, it's uniformly distributed mass, so the center of mass is pretty much right in the center of that brick, or whatever it is. But now, since it has this tilt to it overall, that center of mass is no longer over the base of the object, that side that's resting on the surface. So now it's going to want to tip over. This is an unstable situation on the right here, so it wants to fall over like that. And you can see this sort of in action with like a can of soda or any kind of can, where if you take that can, well, if it's full and you just stand it straight up, then it's full, it's all fairly uniformly distributed, so the center of mass is pretty much in the center of the can. You stand it on its, like it's normally just stand it up, that center of mass is directly over the base, fine, just be stable like that. If the can's still full, and you try to put it on the sort of the bottom rim of it, right, you do like something like that, the center of mass is now no longer over the base, and it's going to fall over. What is kind of a little bit of a trick, or I don't know, party trick, whatever you want to call it, that if you actually drink most of the liquid in that can, such that you leave just a small portion, when you tip the can over, that small portion actually is most of the weight of the can, and so the center of gravity of that portion is essentially the center of gravity of the can, and if you have just the right amount, then that center of gravity can be right over the bottom rim, and the can will balance on that rim. So it'll just stand at a very awkward looking angle, just like that. So yeah, feel free to try that if you haven't never done it before. It's interesting. Drink just most of it, leave a couple of sips at the end, and try putting it on the rim. Okay, so question then, just about center of mass, center of gravity, same difference. Sorry, same thing. I want to say the same difference. If you have these three trucks and they're loaded up with some kind of cargo, but their cargo is loaded up in different ways such that the center of gravity or the center of mass of each of these trucks is in different places, as indicated by those red X's there, which of those trucks is stable and which ones are going to tip over? Let's go ahead and give that a shot. What do you think? Well, hopefully you said only the truck on the far left would tip over, right? So if we draw a line from the center of mass of the truck straight down, that line doesn't go through the base. That means that center of gravity or the center of mass of the truck is not over the base of the truck. It's unstable, it wants to tip over. All the other two trucks, center of gravity has moved over a bit, and now it's over the base. This one, center of gravity is way over, somehow they pushed all the stuff into the top right corner, and now it's definitely over the base, it's stable. So another place where understanding center of gravity is useful, or where it might not matter if you understand it or not, but you see why something works the way it does, is if you're on a balance beam, or just trying to balance on anything in general, you sort of naturally will tend to want to put your arms out. And the reason that this is useful is sort of twofold. For one, going back to rotation, remember when you're when the mass of you is distributed more or further away from the axis of rotation. So if I'm going to fall off a balance beam, I'm essentially rotating around the balance beam. That's where the axis of rotation is, right? So if I take my arms and I put them out, then I've now distributed my mass further away from that axis. That means I've increased my rotational inertia, which makes me harder to rotate. Right? So there's one thing, or one way that putting your arms out helps. The other way has to do with your center of gravity. Right? So when you put your arms out, or maybe when I only put one arm out, or put both of my arms out to one side, right? By doing that, I can change where my center of gravity is. Right? So normally if I'm staying like this, my center of gravity is probably somewhere, I don't know, in the stomach area, abdomen maybe a little bit up here. Right? When I put my arms to the side, I can shift it over a little bit that way. Right? Or put my arms to that side, I can shift it over that way a little bit. Right? And as long as my center of gravity is over the base, so if it's over the beam, then I'm going to be stable. I'm not going to fall over. So there you go. Rotational inertia and center of gravity in action. How do you like that? Okay, so the final thing to mention when talking about gravity, has to do with ocean tides, or the tides, high and low tides in the ocean. And well, I'm not a biologist or anything like that, but I'm pretty sure that if we didn't have our ocean tides, that life might be a bit different on this Earth. So it's pretty important. And essentially the ocean tides are caused by the gravitational pull of mostly of the moon on the Earth, right? And particularly on all the water on the surface of the Earth, right? There's also an effect from the sun, because the sun has a gravitational pull on the Earth and the water on the surface of the Earth too. But we'll just think about the moon for a minute, right? So what happens when, say, the moon is on one side of the Earth here, and remember the Earth is rotating around its axis at the same time that the moon is rotating around it, but just take a kind of a snapshot, right? Earth's here, moon's here. The moon is pulling on the Earth, and it's also being pulled by the Earth. But it's also, on a more detailed level, it's pulling on all the water on the surface of the Earth. And since the water is liquid, it can deform and move around and get pulled by that moon. So when you're on the closer side to the Earth, all that water is feeling a pretty strong gravitational force from the moon. So it actually gets pulled towards the moon a little bit. Right? So that's why we have a high tide on the side facing towards the moon. On the opposite side of the Earth, it turns out the Earth is very large. So when you go from one side to the far side, the distance is very great. And remember, the force of gravity falls off as the square of the distance. So on the far side of the Earth, the force of gravity from the moon on the oceans on the far side is much weaker than it is on the facing side. What that means is that the far side essentially feels less of a force of gravity, and so it doesn't get pulled as much, and it actually is able to extend out a bit. In a way, it sort of pushes itself out a bit. Right? So that's why you have high tides actually on the side of the Earth that's facing towards the moon and the side that's away from the moon. And then on the other sides, you would have be in between somewhere. Or low tides when you're right on the 90 degrees from that. So it turns out, like I said, that the sun also plays a role in the ocean's tides, which is why it's not always as straightforward as just saying, oh, I see the moon right there, there's a high tide, because the sun is also playing into that too. And so the time that you do get the highest, or the greatest high tide, so they call it king tide, I think, is when the moon and the sun are on the same side of the Earth, because they're all those effects I just told you about happening with the moon and the Earth, happening with the sun and the Earth too. So when the moon and the sun are on the same side, we essentially amplify that effect. We get an extra effect from the sun. Also, that happens if the moon and the sun are on opposite sides, right? Because again, it's the close side of the Earth and the far side of the Earth that has a high tide. So when the sun's on the far side, then you get that same effect on the close side and the far side. Again, we still have those two effects working together to create that king tide. All right, I think that's about it. That's all I got for this lecture on gravity. Hope it was interesting. And yeah, I definitely recommend going and trying out that inverse square thing for yourself. Just take 2 pieces of paper and fold one of them twice and try figuring out where they look the same size to you. Yep. All right, well, I will see you next time.